Hello everyone from Math 2000, Linear Algebra. It's Professor Winson here again with a video on your Zybooks section 8.2 titled Eigenspaces. Now we've actually seen in section 8.1 I've written out some examples of eigenspaces, but I just didn't actually call them that. So you'll see what I mean when we get into it. All right. So for an n by n matrix A, the set of all possible eigenvectors corresponding to a single eigenvalue, also with the zero vector, they mention this later. All right. So the set of all possible eigenvectors that correspond to a single eigenvalue, along with the zero vector, forms a subspace of Rn, right? A vector space in its own right. This fact brings up issues normally associated with new vector spaces, such as proving the set is a subspace, right? Is it non-empty, closed under vector addition, closed under scalar multiplication? Finding a basis for the subspace. And what you're going to see in a minute is that finding a basis for these eigenspaces is going to be exactly the same as finding a basis for the null space of some matrix. And also looking for applications. All right, great. All right, so they give us here the definition of an eigenspace. So if the pair, lambda and a vector x are an eigenpair of matrix A, remember eigenpair? Well then, and this was mentioned in section 8.1 as well, so is lambda and the vector k times x, where k is any non-zero scalar. Alright, so here's the definition of an eigenspace. The zero vector, along with the set of all eigenvectors corresponding to an eigenvalue lambda, is called the eigenspace of A corresponding to lambda. And it's denoted with this capital E with a subscript of lambda, and then in parentheses, the matrix A that we're looking at. The eigenspace of A corresponding to lambda. And they go over here showing you that this set of vectors, if you have the zero vector along with the set of any eigenvectors making up this eigenspace, it's actually a subspace of Rn. All right, it's non-empty because the zero vector will be in there, and it'll be closed under vector addition. It'll be closed under scalar multiplication. All right, so you can read this. It's a pretty short proof. Okay. So suppose A is a 3 by 3 matrix. The eigenspace, of A corresponding to lambda is the null space of the matrix A minus lambda I. If you recall, I'll pull up some paper here. Remember, if we have a matrix A, and remember this was brought up in section 8.1 as well. If I want to say, well, if x is an eigenvector corresponding to an eigenvalue lambda, that means that this equation is true, right? Again, the vector x would be an eigenvector as long as it's not, if x is not 0, right? If this vector is not the 0 vector, and this equation is true, a times x is equal to lambda times x, then they call x an eigenvector, corresponding to eigenvalue lambda. And do you remember how this equation got manipulated? if I want to make sure, set it up so that both sides are some matrix equation, lambda times the vector x would be exactly the same as lambda times the, identity matrix times vector x, and then subtracting from both sides and factoring out vector x, right, we got this, right, a minus lambda I times vector x would be equal to the 0 vector. All right. The eigenspace. The eigenspace of matrix A corresponding to, lambda, corresponding to eigenvalue lambda, is just the set of all the solutions to this equation. Again, even the 0 vector belongs to these eigenspaces, right? So it's again the 0 vector and all the eigenvectors. All the solutions to this equation, a minus lambda I times x equals 0, all the vectors x that make that true. So the eigenspace of A corresponding to lambda, which is this, E sub lambda of A, is the set of all these solutions. It's all these vectors x such that A minus lambda I times x equals the 0 vector. And this may look familiar, right? When you're talking about what vectors do I multiply a matrix by to get the 0 vector, remember this was also defined as the null space of that matrix. So yes, that first statement in the activity is a true statement. So this is true for any eigenspace, right? So the eigenspace of a matrix, a square matrix, corresponding to a specific eigenvalue lambda, is just the null space of the matrix A minus lambda I. And you talked about, in chapter 7, also chapter 6, I believe, finding the null space of a matrix. Okay, so this is true. And then lambda is an eigenvalue of A if and only if the null space of A minus lambda I consists of only the 0 vector. No, that's not true, right? The null space, again, back here, this equation, right, we're looking for, because remember, these values of lambda, these eigenvalues, are set up so that the determinant, right, remember, we want the determinant of A minus lambda I to be equal to 0. So that way this equation has more than just the 0 vector as a solution. Okay, so the eigenspace corresponding to our particular eigenvalue should have more than just the 0 vector in it. Right? So yeah, this is not happening. That is false. How about lambda is an eigenvalue of A if and only if the rank of A minus lambda I equals 3. Now remember, this was a 3 by 3 matrix. Well, no, this is basically the same statement as the previous one. Remember the rank nullity theorem? The rank of A minus lambda I is 3 means that the nullity of A minus lambda I would be 0. Remember, rank plus nullity would equal the number of columns. And if the nullity is 0, well, that would mean the null space of A minus lambda I consists of only the 0 vectors. So these two statements are actually the same thing and therefore both false. How about lambda is an eigenvalue of A if and only if the determinant of A minus lambda I equals 0? Well, I just said that one. a second ago. This is a true statement. Right, lambda is an eigenvalue of A if and only if it's a solution to this. Remember, this is the characteristic equation for A. And then if it's a 3 by 3 matrix, right, you can have at most 3 distinct eigenvalues. That's true, and you saw this in section 8.1. An n by n matrix can have at most n distinct eigenvalues. So this is true for a 3 by 3 then. Okay. All right, and then an eigenbasis is any basis for the eigenspace of A corresponding to lambda. And remember, this eigenspace of A corresponding to lambda is just the null space of A minus lambda I, right? So if you can find a basis for that null space, you'll also have found a basis for this eigenspace, right? Same thing. And like they're saying here, finding an eigenbasis is found by solving A minus lambda I times x equals the 0 vector, finding a basis for this set of solutions. And you did this before when finding a basis for the null space of this matrix. And again, this is the matrix A minus lambda I we'll be doing this for. Alright, so I'll do this first example with the 3 by 3, and then you can read example B on your own. Alright, so here's the matrix given in example 8.2.1 part A. And it's a 3 by 3, and they're asking us to find a basis for this eigenspace of A corresponding to lambda equals -2. So remember, I said a second ago, this eigenspace of A corresponding to lambda equals -2 is simply the null space. The null space of A minus lambda I. Well, lambda is -2, so A minus -2I, that'd be A plus 2I. Alright, so here they've already did the, solved the characteristic equation for us, and they told us -2 is an eigenvalue of this matrix. We don't have to do that, right? Well, remember, if I want to find the null space of A plus 2I, aka the eigenspace of A corresponding to lambda equals -2, we're going to be solving, finding the solutions of this equation, right? We're going to find what vectors can I multiply A plus 2I by to get the 0 vector. So we're solving A plus 2I, right, that's the A minus lambda I, times, what vectors x would give me the 0 vector. Alright, so what does A plus 2I look like? Well, that's just adding 2 down the main diagonal. Right, and every other entry stays the same. So this matrix, again, just adding 2 down the main diagonal would give me 3, -3, and 3. And then all the other entries remain the same. Right, and my vector x would have 3 components. This is a 3 by 3 matrix. So say x1, x2, and x3. And I want this to be equal to, the 0 vector. Okay, and then this corresponds to, now what I'm going to do is I'm just going to put this into, I'm going to augment the matrix, have this coefficient matrix on the left, the column of zeros on the right. And, you can do some row operations here. Now you can go to the calculator if you want. I'm going to basically just put this 3 by 3 matrix into reduced row echelon form. Which, again, you can go to the calculator here, do it by hand, but this is very easy to see for me. I can get rid of this row by just adding the first row and second row. Right, that'll become all zeros. If I take the opposite of the first row and add it to the third row, now the third row is all zeros. And then to make sure the leading entry is a 1, get that pivot, that lead 1, I'm going to multiply the top row by a third. So we end up with this. That'll be 1, 1, 1, and then again the column of zeros over here after the bar, and then the other two rows become, all zeros. All right, and then looking at this, we can see our, pivot. Look for our pivot columns, right? This is a pivot, the leading ones in these rows. So x1, right? The variable x, these are the coefficients of x1. x1 is a basic variable, and then these two columns, right, are not pivot columns. So those correspond to my free variables. So x2 and x3 are free variables. I can let them be any real number I wish. Now you've seen me do this plenty. I like to replace my free variables with some other parameter, some other letter. So I'm going to let x2 be represented by the letter S, and I'm going to let x3 be represented by the expression t, right, where S and t are any real number I want. Alright, well then from that, the only equation that, the only row that really means anything here that helps us find solutions, this is 0 equals 0, this is 0 equals 0, those aren't, you can ignore those, is this first row. And the first row is stating that x1, right, 1x1, plus x2, which I'm calling, S, plus x3, which I'm calling t, is equal to 0, and then I can solve for x1, in terms of these free variables. So x1 would have to be the opposite of s, minus t, just subtracting s and subtracting t. So there we have it, right? Now I can state the solutions to this equation, this, a plus 2y times x equals 0, and therefore find the null space of a plus 2y, or this eigenspace of a corresponding to -2. They're all the same. So the solutions are the following vectors, right? My x1, x2, x3, right, equals, x1 I said was negative s minus t, and then x2 is s, x3 is t, and you've seen me do this before as well. I'll split these up, write it as a linear combination involving this s and t. Right? This is s times the vector -1, 1, 0. Right? Those are just the coefficients of s going down these components, plus t times the vector -1, 0, 1. Right? So it looks to me that every solution to this equation, every vector in the null space of this matrix, in other words, every vector in this eigenspace, is a linear combination of -1, 1, 0 and -1, 0, 1. So I'll write this out. So the eigenspace of A corresponding to lambda equals -2 is the span of the set with these two vectors, right? The -1, 1, 0 and -1, 0, 1. So there's the eigenspace that we're looking for. And then this set with these two vectors therefore form they form a basis, right? Every vector in here is a linear combination of these two, and they're independent. So again, a basis, right? Bases aren't unique, but a basis for this eigenspace, in other words, an eigenbasis, right? They're calling these eigenbases, is just this set with the vectors -1, 1, 0 and -1, 0, 1. And there you go. Right. And since this, so I'll circle all this. And since this basis has two vectors in it, we would say that the dimension, right, the dimension of this eigenspace is 2. Right? It is a two-dimensional space, so like a plane in R3, right? Because all these vectors are 3 components. This is a subspace of R3. This eigenspace would be a plane, a two-dimensional space in R3. And we'll see in a little later, this dimension of the eigenspace, how I said the dimension of this eigenspace corresponding to lambda equals -2, the dimension is 2. This number 2 here, the dimension of the eigenspace, is going to be called the geometric multiplicity of lambda equals -2. The geometric multiplicity of that eigenvalue, okay, is just the dimension of the eigenspace. And we'll see this later in this section. Alright, so hopefully you could follow all that. Again, you've done this plenty of times before. Alright, hopefully by now, finding the null space of a matrix. Only now it's called something else as well. Alright, this eigenspace of a matrix, corresponding to a certain eigenvalue. Alright, so you can read through here. I just did all that. Right. Now this one they do a little, it's a more complicated example because it has, the eigenvalue has a square root in it, but it's still the same setup. Look at, a minus lambda I, and then, put that a minus lambda I into reduced row echelon form, and find the solutions to this equation here, where you're basically, again, finding the null space of a minus lambda I. Alright, so now this next activity, we're asked to determine whether each statement is true or false. So you're given these 3 by 3 matrices, A, R, and M here. And you're just simply asked, is the given set of vectors an eigenbasis for a certain eigenspace? Alright, so I'll just do this first one and I'll leave the other 2 to you. Alright, so again, let's just go over this one more time. I'll write this matrix A down, and let's find the eigenspace of A corresponding to lambda equals 3. So apparently 3 is an eigenvalue of A, right? I'm not going to go in and actually find the eigenvalues this time. Okay, so same deal. I gave a matrix A. It's another 3 by 3. It's got to be square. They're telling us that 3 is an eigenvalue. Maybe you can see that right off the bat too, because if I subtract 3 down the main diagonal, you see how the second row will be made up entirely of zeros? So the determinant, right, of a minus 3i would be 0, and that's what we want when we're trying to find eigenvalues. So 3 is an eigenvalue of this matrix, and we're asked, first I'm going to find this eigenspace, right? What's the eigenspace of A corresponding to lambda equals 3? And like I said, this is the same thing as the null space. It has the same vectors as the null space of A minus 3i. Right, and if I'm trying to find the null space of A minus 3i, means I'm solving this equation, right? Take A minus 3i, and I'm trying to determine what vectors x, can I multiply that by to get the 0 vector. Alright, so A minus 3i, again, just subtracting 3 down the main diagonal. So I'd have 4, 0, negative 8. Right? And then all the other entries stay the same. Okay. And then times again, I'll just write vector x here. You know it's got to have 3 components. and I want this to be equal to the 0 vector, again, with 3 components, 3 zeros. And then to do this, I'll put this matrix into reduced row echelon form. Again, you can use a calculator if you wish, but again, this one's pretty simple. There's already a row of zeros, and you see the first row and the third row are the same, so I just take the opposite of the first row, add it to the third row, and then the third row will become all zeros. And then to get that leading 1 entry, I multiply the top row by a fourth. Alright, so I've just described out loud all the row operations I'd perform. So a fourth of that top row would be 1, -2, -2. Again, we'd have a column of zeros on the other side, and then the row of zeros again. Right? Again, this doesn't always happen with 2 rows of zeros with a 3 by 3 matrix, but it just so happened to work out this way for these examples. Alright, and then just like before, I identify the basic variables, which again would be x1. And as with the last example, my second component and third component are free variables. And like I like to do, I'm going to let these free variables be represented by some other parameters, some other expressions that can take on any real number. So I'm going to say x2 is s again, and x3 is t again, where s and t can again be any real number I wish. They're free. Alright, then from that first row, we're seeing that 1x1 minus 2x2, or minus 2s, minus 2x3, or minus 2t is equal to 0. So I'm getting x1 equals 2s plus 2t. Alright, then the solutions to this equation, right? The vectors in this null space, also the vectors in this eigenspace, same thing, look like the following. So again, my solutions here, x1, x2, x3 look like the following, right? x1 we said would be 2 times my choice of s plus 2 times my choice of t. x2 would be whatever I choose for s, x3 would be whatever I choose for t. And then as before, 2 free variables, I can write this as a linear combination of some vectors involving those free variables. We'd have s times the vector 2, 1, 0 plus t times the vector 2, 0, 1. Okay, so based on all this work, it looks as though the eigenspace of this matrix corresponding to lambda equals 3 is the span, right, the set of all linear combinations of these two vectors, right, of the set with vectors 2, 1, 0 and 2, 0, 1. And therefore this set of vectors here would be a basis. If you do everything, get down to reduced echelon form like this, these vectors you find should form a basis, should be independent. Right? So here's an eigenbasis. A basis for this space is just the set with those vectors 2, 1, 0 and 2, 0, 1. Again, this isn't the only basis. Alright, if I had any multiples of these vectors, these two vectors, it would still form a basis for this space. If you had, replaced one of these with a linear combination of them, and still have two vectors in it, you'd still, as long as they were independent, you'd have another basis, right? So this isn't the only basis. And then again, the dimension of this eigenspace would be 2 again. And therefore they would say that the geometric multiplicity of lambda equals 3 was 2, right? The dimension of this corresponding eigenspace. Anyway, that looks like this set of vectors here, so this is true. Right. Okay, and then again, I'll leave these last two to you. Now, again, the matrices are called R and M, so you're looking at R minus lambda I, M minus lambda I, right, instead of A minus lambda I. It doesn't matter. You can call them A again if you want. Right. And then there are these matrices up here. All right. And then, like I said, I already mentioned the words geometric multiplicity before. Well, you have two different kinds of multiplicity for any particular eigenvalue. So two types of multiplicities are associated with an eigenvalue. The algebraic multiplicity of an eigenvalue, lambda, is the number of times the eigenvalue repeats as a solution in the characteristic equation. Right, so remember, when you're solving that determinant of A minus lambda I equals 0 to find the eigenvalues, the multiplicity of a particular root, of a particular solution, is called the algebraic multiplicity of that solution, of that eigenvalue. And as I've mentioned already, I haven't mentioned this, I mentioned geometric multiplicity, sorry. So an eigenvalue's algebraic multiplicity is indicated by the power of the corresponding factor in the characteristic equation, right? So this algebraic multiplicity is the multiplicity you're familiar with from, maybe pre-calculus class or a previous algebra class, right? When you talked about the multiplicity of a zero of some polynomial, of a solution to a polynomial equation. So this is your typical, the multiplicity you're used to. Now the new one is one I've mentioned, the geometric multiplicity of an eigenvalue is the dimension of the corresponding eigenspace. Right, so like I had that example a second ago, right? So here, right, the dimension of this eigenspace of A corresponding to lambda equals 3 is 2, right? Because a basis had two vectors in it. And I mentioned this in my earlier example. This 2 would also be called the geometric multiplicity of lambda equals 3. Right. Okay. Now there's a nice relationship between algebraic multiplicity and geometric multiplicity, which they state in the theorem below. So the geometric multiplicity of an eigenvalue lambda is always going to be less than or equal to the algebraic multiplicity of lambda. Right. So the dimension of the corresponding eigenspace, corresponding to lambda, will always be less than or equal to the algebraic multiplicity, which they're calling M here. All right, now they do go through some proof here. I'll let you read this and see if you can make sense of it. If not, I wouldn't worry so much about it. Just remember the result. I'm not going to require you to prove this for me. So just remember that the geometric multiplicity is always less than or equal to the algebraic multiplicity. All right, now I haven't shown you any examples of algebraic multiplicity, so let's get into one. All right. So here's a very simple example, right? Because look at this. This is a lower triangular matrix, so it's very easy to state the characteristic polynomial and the multiplicities of the eigenvalues, as I'll show you on paper here in a second. So you see here the matrix given to us in this example. Now this is a lower triangular matrix, right? Because the only non-zero entries are either on the diagonal or below it. Right? Everything above the diagonal is a 0. So this is one of those lower triangular matrices. So if you recall from section 8.1, the spectrum of an upper triangular or a lower triangular or simply a diagonal matrix, the eigenvalues were just the values down the main diagonal. So the spectrum of A, the set of all the eigenvalues, well, 2 and 5. Right? Now the algebraic multiplicity is just how many times that eigenvalue is repeated as an eigenvalue. So 2 only shows up once down here, right? So the algebraic multiplicity of the eigenvalue 2 is 1. Right, again, because it's only repeating one time. Whereas for the eigenvalue of 5, the algebraic multiplicity would be 3. Right? You see 5 repeating 3 times here. So the algebraic multiplicity of 5 is 3. Now you could also see this if you write out. Now not every matrix is lower triangular or upper triangular. Really easy like this. Look at the characteristic equation. Right, determinant of A minus lambda I. Right, when is that equal to the number 0? And again, A minus lambda I, you're just subtracting lambda. So you have 5 minus lambda, 2 minus lambda, 5 minus lambda, 5 minus lambda down the main diagonal, and all the other entries remain the same. Now it's still going to be a lower triangular matrix, and remember the determinant of a triangular matrix was just the product of those main diagonal entries. So this left side, the characteristic polynomial, you'd have 5 minus lambda 3 times. So 5 minus lambda cubed multiplied by, and then you have this one factor of 2 minus lambda, and again this is equal to 0, and then you can see the solutions are 2 and 5, right? Lambda equals 2, lambda equals 5, giving me the spectrum of A. And what they were saying in the Zybooks section was, look, when you factored the polynomial completely, right? When you factored the characteristic polynomial completely, just look at the powers. All right, you see the power of 3 there on 5 minus lambda. So that means lambda equals 5, right? That eigenvalue has an algebraic multiplicity of 3. And then the power on 2 minus lambda is just, 1. It's only one factor. And again, look at the power on that. So the algebraic multiplicity of lambda equals 2 is 1. Right, so again, just the number of times it repeats as a solution to this characteristic equation. Now in this example, we're asked to find the algebraic multiplicity of each eigenvalue, which we just did, right? 1 and 3. But also the geometric multiplicity. Now again, the geometric multiplicity is simply the dimension of the corresponding eigenspace. Alright, so let's get into those. So I got algebraic multiplicities there. Let's get into finding the geometric multiplicities. And this is going to end up being the same exact thing I was doing in earlier examples in this video. Multiplicities. Okay. So I'll start with lambda equals 2. Now the algebraic multiplicity of lambda equals 2 is 1. And you saw in that theorem a minute ago, the geometric multiplicity is going to be less than or equal to the algebraic. And I'll tell you right now, all these eigenvalues, their corresponding eigenspaces are never going to be just the zero vector. Right, which if it was just the zero vector, you'd have dimension 0, or a geometric multiplicity of 0. I'll tell you right now, for every lambda, every eigenvalue, the geometric multiplicity will be at least 1. So if it has to be at least 1 and can't be greater than 1, I'm going to tell you right now, the geometric multiplicity of lambda equals 2, let's say geometric mult, is going to be 1. I promise you this. Now let's actually show it. Show that the dimension of the corresponding eigenspace is 1. Alright, so let's find, like I was doing earlier, the eigenspace of this matrix corresponding to lambda equals 2, which again is the null space of the matrix A minus 2I. Alright, so I'm going to be solving this equation, finding the vectors such that, when I multiply A minus 2I by those vectors, I get the 0 vector. Now these will be with 4 components, right? This is a 4 by 4 matrix. Alright, so what does A minus 2I look like? It's just subtracting 2 down the main diagonal. So we've got 3, I just said, subtract 2 down the main diagonal. 3, 0, 3 and 3. And then every other entry remains the same. Okay. And then you have, again, some vector x with 4 components equals the 0 vector with, 4 zeros. Alright, and then I would put this into reduced row echelon form. And again, you can use a calculator, or, this one again isn't so bad. Because look, I would do this, right? I'd move this row up top to get, 1, 2, 1, 3. And then eliminate, maybe switch the first and the fourth row, then multiply the top row by -3, and then add it to the bottom row. That'll make another row of zeros, so you have 2 rows of zeros. And then this would be a pivot. I move this to the second row, multiply by a third, and then I'll get this 1, 2, 0, 3. Then again, this second row would, I'll move this third row to the second row and multiply it by a third to get the pivot 0, 0, 1, 0, and then a couple rows of zeros. Actually, this doesn't look right. Alright, I'm just going to punch in the calculator. I should either do it by hand, write it out, or come up with the calculator. Alright. So I'm going to enter this 4 by 4 matrix and put it in reduced row echelon form, come back when I had that. Okay. So yeah, that's a lot better. I was like, I knew the geometric multiplicity had to be 1. I was like, oh, the way I'm doing this, it has 2 free variables. So you see on my calculator there, it's 1, 0, 0, 0. 0, 1. Oh yeah, because if I took -3 times this, added to that, it would all of a sudden put a non-zero entry there. See, I was rushing it in my head. Right, 0, 1, 0, and then 1.5, which is, 3 halves. 1.5. Right, so that's 3 halves there, sorry. Then 0, 0, 1, 0. There, we got the 3 pivots. And then a row of zeros. Alright, so that's better. Alright. So again, I look at my, the first component, the second component, the third component, right? These are all pivot columns. So x1, x2, x3 are all basic. It's this last column that doesn't have a pivot, right? So x4 is free. And as I like to do is, I'm going to replace x4 be some expression, some other expression that can take on any real number. And I'm noticing a fraction in here, 3 halves. I want to get rid of that denominator. When I'm going to replace x4 with something that's a multiple of 2. Right? So instead of just t, I'm going to replace x4 with 2t, where again t can be any real number. So therefore 2t could be any real number I want, right? x4 needs to take on any value. So this still does. Alright, and then from each row here, I'm seeing that x1 has to be 0. From this row, we'd have x2, right, 1x2 plus, now 3 halves x4. But 3 halves times 2t would be 3t equals 0, meaning that x2 would have to be the opposite of 3t, right? My choice of t. Oops, let's get rid of the calculator here. Yeah, x2 would have to be the opposite of 3t. And then from this third row here, x3 also would have to be 0. And like I said, x4 is 2t. So I'll write the solutions to this, right? So hopefully you can see, I'm actually just going to write the eigenspace. So the eigenspace of A corresponding to lambda equals 2 is the span of just a single vector, right? There is only one free variable, t. And, the coefficients of t throughout this are 0 for x1, -3 for x2, 0 for x3, and then 2 for x4. Right, so every vector that's a solution to this equation is a multiple, some multiple of this vector here with the 4 components 0, -3, 0, and 2. And then a basis for this, right, an eigenbasis, would be just this set with this one vector in it. Therefore, the dimension of this eigenspace is 1, as I was hoping for, right, as I suspected. So like I said, this takes me way back to the beginning. So the geometric multiplicity of this lambda equals 2 is 1, right, because that's the dimension of the corresponding eigenspace. And notice again that the geometric multiplicity is less than or equal to the algebraic multiplicity, right? The geometric multiplicity was 1. The algebraic multiplicity for lambda equals 2 was also 1. Okay, so now let's look at 5. Right, let's do the same thing for lambda equals 5. Right, so again, I'm doing geometric multiplicities here. Let's get rid of all this paper. Okay, so now for lambda equals 5. So again, we're finding what's the eigenspace of A corresponding to lambda equals 5, or the null space of A minus 5i. Same thing. All right, so I look at this equation, right? A minus 5i times what vector is x? Again, a vector with 4 components. When will that give me the 0 vector with 4 zeros? All right, so I'm going to do what does matrix A minus 5i look like? So that's just subtracting 5 down the main diagonal of A. So you have 0, -3, 0, and 0. And then everything else is the same. So 0 here, 0 here, 0 here, 0 here, 0 here, 0 here, 0, 0, 0, and then 1, 2, 1. Okay, so lots of zeros in this one. Times, again, some vector x with 4 components, say x1 through x4, equals a bunch of zeros. And as before, I'm going to put this into reduced row echelon form. And, so I'd move this up top, keep this as the second row, change it to 1, make that, there'd be 2 pivots here. And then get zeros above that. Alright, so I think it's going to be 1, 0, 1, 0, 0, 1, 0, 0, and then a couple rows of zeros. Now I'm just going to verify that. Alright, again, I'm doing this in my head here. There's a lot of zeros though. This one may be a little easier, but let me just go back and let me just change that last 4x4 matrix I made into this 4x4 matrix, which will be really easy because it's just a bunch of zeros. So I got 0 there, zeros across the top row. This is -3 now. And zeros there. And the whole third row is zeros. And the fourth row is 1, 2, 1, 0. Alright, and then I go reduce row echelon form again. Yes, so that's what I said. Great. Again, so top, 1, 0, 1, 0. Again, you're going to have these 4 zeros on the other side. And 0, 1, 0, 0. And then a couple rows of zeros, which we're going to ignore, because that's just 0 equals 0. That's fine. Alright, so again, I identify my basic variables, which would be x1 and x2 that correspond to these leading ones, these pivots. And so these two columns don't have a pivot, right? Don't have one of those leading ones in it. So x3, x4 are free. And as I like to do, I'm going to have x3 be replaced by, say, s. I'm going to have x4 be replaced by some other expression, t, where s and t are any real number. Alright, then from that first line, we see that x1 plus x3, right? So x1 plus s must be equal to 0, meaning that x1 will be the opposite of s. And then this second row just tells me that x2 must be 0. Alright, so again, 2 variables here. So, and I'm just going to write the actual span. I'm going to write the eigenspace right now. So the eigenspace of this matrix corresponding to lambda equals 5 is the span of the set with the following 2 vectors, right? One corresponding to each free variable here. The 1 vector, has components that are coefficients of s, so -1 for x1, then 0, then 1, then 0. And, the other vector corresponding to the coefficients of t, 0, 0, 0, 1. And every solution to that equation earlier is just some linear combination of these 2 independent vectors. Therefore, this set is a basis then, right? An eigenbasis. The set with these 2 vectors is a basis for this eigenspace. Therefore, the dimension of this eigenspace is 2, and that is called, again, the geometric multiplicity of lambda equals 5. So I'll just do geom mult. Right. That's the geometric multiplicity of lambda equals 5. And notice, the geometric multiplicity of lambda equals 5 was 2. The algebraic multiplicity of lambda equals 5 was 3, which is going to happen sometimes. But still, this holds. Remember, I'll say it one more time here. The geometric multiplicity of some eigenvalue will always be less than or equal to. Right, we saw a case of each. For lambda equals 2, the geometric multiplicity and algebraic multiplicity were equal. They were both 1. For lambda equals 5, we have the case where the geometric multiplicity is less than the algebraic. But one of those is going to happen. This is going to be always true for any value of lambda, for any eigenvalue. Okay? Wonderful. Right, again, you can read through. They go through the same kind of stuff I just did here in this example. All right. So I'll leave the activities to you. All right, now here they're giving you the characteristic equation. So stating the algebraic multiplicity of a specific eigenvalue should be very simple. Stating the geometric multiplicity is a little tougher, right? Because again, you got to figure out the dimension of the corresponding eigenspace. Here's another one that's pretty simple because it's an upper triangular matrix, so you can very easily state the algebraic multiplicity of an eigenvalue. But then again, the geometric multiplicity, a little tougher, a little more involved, because you have to find the dimension of the corresponding eigenspace. All right, and then your challenge activities are, there's only 3 levels here. You're asked for eigenvalues and their algebraic multiplicities, which, this example I'm looking at here is, again, very simple because it's lower triangular. The next level. So again, now here they're not even giving you a matrix. They're just giving you the characteristic equation, right? What you would use to find the eigenvalues. So factor this polynomial completely, I would suggest by grouping, factoring by grouping. And state the solutions to that equation. What are those eigenvalues, and what are their, how many times do they repeat? What are their algebraic multiplicities? And then the final level is oh, what a joke! What a joke! You're given eigenvalues of some matrix. You're given a basis for the eigenspace corresponding to those eigenvalues, and then ask for the geometric multiplicity. Well, if you already know a basis for the corresponding eigenspace, then you know the dimension, and if you know the dimension, that is the geometric multiplicity. So pretty easy examples, in my opinion. Pretty easy challenge activity. If, again, you know what those words mean, algebraic multiplicity and geometric multiplicity. Then you have your exercises. Again, some of these are on your assignment. Some are not. I would still, even if they're not assigned, I would still recommend looking at all of them, trying them all, just to get more exposure to the material, maybe get better at it, more practice. And you can always go back, and if you're getting stuck on something, look at the solution to check yourself. But please, try to hold off on looking at the solutions until you've tried them yourself. Tried working on them, and then look at the solutions. Right? Don't just look at the solution right away and then copy it. Right? You're not going to learn anything if you're not doing anything. And yeah, hopefully this video is a nice guide for you for this section. If you have any questions, of course, send me a message and I'll get back to you as soon as I can. And thank you very much for watching.